Example is taking the possibility of factoring a polynomial and going backwards with it. We're starting here with the roots instead of trying to find them, and we're trying to go backwards to find a possible polynomial off by maybe a product of a coefficient or a product of a constant. So here we're given that there's two roots, -2 and 1 plus 3i. The problem here is this polynomial has real coefficients and it has a degree of 3. Well, if it has a degree of 3, it should have 3 roots. And if it has real coefficients, you can't just have 1 plus 3i as one of the roots. So the third root is its conjugate. It's called the conjugate root of 1 plus 3i is 1 minus 3i, and that's the complex root theorem, that if you have one, you have to have the other. When we set up these roots, we have to make sure that we set it up in such a way that it's always x minus whatever the root is. So the first one is going to be x minus a -2, and I'm going to write it out explicitly. Of course, you could change it to x plus 2, but it helps me write the second 2 out, which would be x minus 1 plus 3i and x minus 1 minus 3i. And I'm not going to distribute the negatives because I'm going to use a neat little trick to help me multiply these last two factors together. And that trick is to rewrite them as let a equal 1 plus 3i and let b equal 1 minus 3i. So I can rewrite those two as x minus a times x minus b, and then just multiply that together to see what I do with these complex roots. So we're going to go x times x is x squared. We're going to go -a times x is -ax. X times -b is -bx. And -a times -b is positive ab. And then I'm going to just factor out two things in the middle here, a minus and the x. And I'm going to do it in such a way that I pull the minus to the front and the x to the back. That's legal because multiplication is commutative, and I can move it one way or the other, it doesn't matter. So I decided to split one to the front, one to the back. And then what's left in here is a plus b. So if I want to find the product of these two binomials, ugly as they are, they're still called binomials, all I have to do is find the sum of my two complex numbers and the product of my two complex numbers and just substitute the answers into those two locations. So first off, let's find a plus b. A is 1 plus 3i. B is 1 minus 3i. And if you add those together, the 3i's are just going to cancel, and you're just going to be left with 1 plus 1, better known as 2. Alright, and then if we do a times b, it would be 1 plus 3i times 1 minus 3i. And since they're conjugates, the product of the middle is going to cancel the positive 3i and the negative 3i. So all we're going to get is 1 times 1 is 1. -3i times positive 3i times -3i is a -9i squared. But I squared just changes the sign of the number, so this is 1 plus 9, better known as 10. So when I come back to the problem, I can rewrite it as x plus 2 times x squared minus a plus b, and a plus b was just 2, so we're going to get 2x, plus a times b, which was 10. And then we just have to multiply the rest of this out. So we're going to get x cubed minus 2x squared plus 10x plus 2x squared. Isn't that interesting? Minus 4x and a plus 20. So altogether, the possible polynomial that has these roots would be x cubed plus 6x plus 20. Maybe off by a multiple, like if you multiplied everything by 2 or multiply everything by -1/3, but this would be the base polynomial that has these roots. And I'm going to call this p of x as a function. And that's it.